Okay guys, welcome to this vodcast on slope fields or directional fields. It's the final installment in our unit on differential equations and differential equation solving. It comes at the topic from quite a different approach, a graphical approach, and I think you'll enjoy it. Now we did begin the unit towards the end of our final lesson of term 2, but I'll be taking it from the start for those who missed out on that lesson or those of you who'd forgotten. Now, just a reminder, there is an exercise in the textbook on this, but it's not a particularly good one. So I gave you the extra worksheet with some very good questions to work through on slope fields. And it also contains Euler method questions that are very useful as well. Okay guys, before we begin our investigation into slope fields, let's just do a quick overview of what DEs, differential equations, are all about. So a differential equation is an equation with a derivative contained in it. So a first order DE is one with a dy dx expression. A second order is with a double derivative involved, and so on. Now in terms of spec, what do we do with DEs? We verify them. That is, we substitute the solution into the left-hand side and the right-hand side and verify, or we solve them. Now, you'll only ever be expected to solve a first-order DE in a spec course. So what does it mean to solve? It means to determine the rule between the variables that satisfies the DE. Okay, now, of course, there's particular solutions where there's no generalized constants and general solutions where there are constants, at least one constant of anti-differentiation. Okay guys, here's a question for you. What can you do if you want to find a particular point on the curve of the solution, that is the value of y for a particular value of x, but are unable to solve the first order DE algebraically? Okay, so in other words, you've got a dy dx equals f of x situation involved. We'll talk about a function of both variables, x and y, in a minute. You're told when x is a, y is d, and you need to find the value of y when x is equal to b. Well, of course, if you've got access to your CAS, you just whack it into that formula and you'll get a very, very good approximation for the value of y when x is equal to b. Okay, what else can you do? You can approximate the value of y using Euler's method and taking a number of iterations. So there's the rule, there's the recurrence relation for successive y values using the previous x and y values, and your initial x and y values take on the initial known point on the curve. Okay, so we've looked at Euler's method in depth. Now, Euler's method also has the advantage that the derivative need not be a function merely of x, and that has the advantage over your CAS calculator, which can't anti-derive a rule with x and y involved. But we can approximate it with Euler's method. So, for instance, if our rule for dy dx is a function of x and y, it could be a function of y alone even, then we can still apply the previous x and y values in the iteration to our rule for the derivative and get the successor y value, and then we add the step size to the previous x value, and so on and so forth. So it works perfectly well with whether our rule for the derivative is in terms of x and y, or in terms of y alone. So it does have that advantage. Okay guys, a third alternative is to use a directional field or a slope field, facilitating a graphical solution as opposed to an analytical or algebraic solution. Now, what is a slope field, which is the focus of our vodcast today? Basically, we take a window on the XY plane and we take discrete XY points, so discrete XY points, and we substitute those XY pairs into our rule for dy dx, and that gives us a steepness value. So if it's positive, we draw a short positive line segment representing that value, and if it's negative, a negative short line segment representing that value. Let's have a look at an example. So bringing up Why aren't you clicking forward? Ah, because I'm in the pen mode. Okay, here we go. Here's the example. Okay, so our dy dx is a very simple one. It's a very simple solution, but this is just an example. That represents the slope field for that particular differential equation. Let's examine it in closer detail. So let me just grab my red pen. Let's have a look at this point. The slope representing the line segment representing the point -1, 2. So there it is there, just to highlight it. Okay, so if I was to replace, to substitute x equals -1 and y equals 2 into my rule, in fact this rule is involving x only, so in fact if I was to replace x equals -1 into my rule, 1 on x squared, I get a value of 1. So that slope, that little line segment, is representing a steepness of 1. Let's take another point here. Let's go for this point down here at 2, comma -1. Okay, so the reflection of the other point about the line y equals x, that's another matter. So if I was to replace x equals 2, y equals -1 in my rule, and as I said, the rule is just governed by x values alone, I get a steepness of 1 on 2 squared, which is a quarter. So that little line segment should appear flatter than the other one that we looked at before. That represents, so this one represents a steepness of 1, and this one represents a steepness of 1/4. Both positively sloped. Now, in fact, if you have a look at all the little line segments making up this slope field, they're all positively sloped. Why would that be? Have a look at the rule. No matter what value of x I plug into the rule, it's always going to have a positive value. Let's now compare that with another example. Dy dx is equal to y, just a function of y, a very simple function of y. Okay, so it's driven by y values only. All right, so let's try to make sense of the slope field as we see it. All right, let's have a look at the point, the slope representing 1, 2, which might be that one there. Okay, so if I replace, if I substitute x equals 1, y equals 2 into the rule, okay, it's in terms of y only, that's representing a steepness of 2. Okay, so dy dx, when I replace y with 2, I get a steepness of 2. If I now compare it to the line segment down here, okay, at the point -1, -1, and you can see if I substitute that point into my rule for dy dx, I get a dy dx value of -1. So there's the line segment representing that steepness, that derivative value. Okay, so that's what slope fields are essentially about. It's a whole bunch of discrete xy combinations within a window on the xy plane, and we can use our rule for dy dx, our rule for our first order differential equation, to actually determine the steepness of how that curve would look at each of those discrete xy pairs. So hopefully that's making sense to you. Okay, graphical solution via a directional field. So the slope field so created facilitates a graphical solution if we have access to some point on the curve. So if we know some x and y value that exists on the curve, we can graphically come up with the solution curve based on the slope field. So what is that all about? So we did a bit of a demonstration in class with people throwing their arms out and corralling others as they're trying to move through. That's exactly what it's all about. So if you move to the right and to the left from that point on the plane, just think of each of those line segments as bumping you up or down or moving you in the direction suggested by their steepness. So it's like a corralling, and I'll show you some examples of that in a minute. So it's actually, there's a bit of an art to it. It's not totally mysterious. I mean, some people's solutions may be slightly different from others, but it should be essentially the same for everybody. So we'll have a look at some examples now. Okay, so here's our question that we're going to begin our discussion with. It's a dE, y dash is of course short for dy dx is equal to x times sine y. And there's its representative slope field for over x over the interval -3 to 3 in the x and 0 to 5 in the y. Quite interestingly, let's have a look at some of its features. So I might just grab my pen now and notice down on the y-axis, so whenever x is equal to 0, dy dx is equal to 0. Why? Because they're all perfectly flat line segments. Do you see that? Every line segment, every slope is perfectly flat, indicating a gradient of 0. Interesting. Where else do you see a 0 gradient? And of course that makes perfectly sense, because if I have a look at my rule for dy dx, whenever x is equal to 0, y dash is equal to 0, dy dx is equal to 0. Now we know sine is also 0 if y was equal to 0, so you're expecting 0 gradient to exist along here. But where else do you have 0 gradient? Of course, when y is equal to pi, you're going to have sine is going to be 0 when y is equal to pi, and that would be this line of flat slope segments as well. So they're all points that in the slope field representing where dy dx is equal to 0. So I thought that just might be interesting to have a look at. So obviously that would be the line y equals pi, because of course when y is equal to pi, sine y is equal to 0, therefore dy dx is equal to 0. All right, let's take all of this and rub it out, get rid of it all, and let's start to look at some solution curves. All right, let's have a look at this first one. So this is saying, suppose on the solution, on the actual solution curve, when x is 0, y is equal to 1. So let's just start there. Okay, so that's the point x equals 0, y equals 1. Now, this is what I meant by the corralling. So as I move to the right, I'm slowly being suggested a direction by each of those slopes. Okay, that's off to the right, and everyone's going to be just slightly different. And as I move to the left, oh, it's a bit hard with, sorry, it's a little bit wonky, but you get the idea. It should look symmetrical anyway. And that would be a very rough sketch of what the solution curve looks like, given that we know a point on the curve is 0, 1. Okay, let's just choose another one. Let's go green. Okay, let's have a look at this one. When x is 0, y is equal to 5. So we're starting up here. What does the solution curve look like? So it's going to look quite different. As I move to the right, it'll look like this, and it should look roughly symmetrical as I move to the right, being corralled, and there would be my solution curve for a curve that goes through the point 0, 5. Okay, so two very different looking curves, but they're appropriate to the initial conditions, if you like, a known point on the curve. Hopefully that's making sense. What I'd like you to do is have a look at that slope, and maybe with a pen in your, or a stylus in your own hand, have a go at maybe one or two of the other ones. That would be great. Okay, let's move on. All right, now I'm not sure if this is going to be entirely useful for you in an exam setting, but you never know. It is possible for your Casio calculator to produce a slope field. So let's consider the same differential equation that we're looking at last time, dy dt. Okay, so our independent variable is t, dy dt is equal to y, so it's a function of y. Now your CAS can actually plot a slope field under whatever window size you wish. So where do you access that facility. Down there from your main menu, diff equation graph, you select that, that button, and then you can type in your DE. Now notice how they're typing it in, Y dash, and I'm pretty sure that Y comes from the ABC menu, Y dash equals variable Y, and as soon as you tap on the slope icon, the slope field icon, a slope field occurs. Now, like in that window, a lot of that slopes have a direction. There's an arrowhead on the end. I don't like that terribly much. You might choose to run with it. That's fine. You can actually edit that. I think it's in Edit. You can actually modify how your slope field appears, and you can have just slopes rather than arrowheads. We can look at that when we're back at school. That's fine. But that's where you access it. Now, you can see in the question, we want to look at particular solutions when y is 2 and x or t is equal to 0. So 0, 2, and when and 1, negative 3. If they go through those 2 points, what would the solution curve look like? So you've got that ability with your CAS as well. You tap the IC window, as you can see indicated there, enter your initial conditions. So you've got XI and YI for initial condition 1, and there you go. So it's going through, so obviously that first one, let me just grab my pen. So here's the first one going through 0, 2, 0, 2, and it's produced the solution curve for you, okay? And for the second one, 1, negative 3, there's 1, negative 3 here, and it's produced the solution curve for you as shown. So there you go. So you've got your CAS that can produce those solution curves for you. It may be useful. I can't think of an exam situation where it is particularly useful, but you have that facility to assist you if you wish. Okay, here's more practice, guys, if you'd like to have another go at this skill. So I might do the first one for you, maybe have a go at the other two. We can compare your results in class when I see you again. Okay, so it's a directional field. We're not given the rule, so it's some rule that we don't have access to, but we can still nevertheless graph the solution given those initial conditions. So I'm going to be working on it with this one. So when x is 0, y is 1, so I'm going to be starting here, moving to the right. I can see that I've got a steepness like that. Moving to the left, I'm just being corralled and moving up in that sort of a direction. So a curve something like that is what you can expect as your solution. So maybe have a go at B and C on your own. If you'd like, I'll have a go at B, and maybe you can do C on your own as well. So pause it if you wish and then come back to it. Let's see how yellow turns out. So here I am at 0, 0. I had quite nicely. Now I'm actually on a slope field. You can see that they're perfectly flat at that point. So all I can do is move along it. And then what am I forced to do? I'm forced to move upwards and follow that line there. And similarly, moving to the right, move along that line like so, something like that. That would be the solution curve for an initial condition. Hopefully yellow's turning out okay for you, starting at 0, 0. All right, it's quite fun. It's the art of sketching a solution curve based on a slope field and an initial condition. So have a go at the last one on your own. Okay guys, what can you expect on the all-important end-of-year exam? Well, it's highly likely, it'll absolutely, out of your 120 marks for exam 1 and exam 2, most likely it'll be a single multiple choice question. That's about it, as it's been for pretty much every year that I can remember teaching Spesh. All right, now there's 2 types of multi-choice questions you can expect. So the first one is pretty much what we've been doing, finding a solution curve or a point on the solution, which is interesting. That's been in vogue the last couple of years for the represented field. So you're told the curve goes through this particular point. Either here's 5 options for the solution curve, or here's 5 options for a point that the solution curve goes through, which has been the recent way to do it. Now the second one is something we haven't looked at, and it's you've got 5 potential DEs matching the slope field, and you've got to choose the right one that matches all the characteristics represented in the slope field. And that's quite fun. The more you practice at these, the better you get. So yes, and it's usually a bit more challenging, but once you pick up the patterns, you'll see how easy it is to actually determine the right answer. Okay, so let's make a start. Okay, unlikely you'll get something this easy, but this is a potential question to get. So here's a slope field, a first order DE, a solution of this DE could be. So it's that first type of question you might get. So you can see you've got a bunch of basic options, and really it's as simple as getting your pen, and let me just change it to red, tracing out a potential solution curve. It's a bit hard to work with a pen with a stylus, and you get the idea. It's a bit wonky, but what sort of curve does that look like? It's a bit of a no-brainer, isn't it? There's only one curve that could match that situation, and it'd be the sine curve. Okay, so that's nothing much to it. Okay, and there is the suggested solution. Okay, here's one more of that easier brand of question, unlikely to get in 2018, but nevertheless, let's be prepared for it. A slope field for a first order DE equation is shown. A solution, that's the key word, a solution could be. A solution. So it's all about tracing a path, a valid, viable path that matches one of the 5 options there, the curve for one of those 5 options. Now, I'm not even going to do it because it should be pretty obvious. We know what the curve of each of those functions look like, and there's only one option that it could be. Hopefully you're onto it, and that option would be the first one, the truncus. So that's the only curve that could match the given slope field. So those kind of questions are very straightforward. Just imagine sketch a solution through the curve and match that, identify that curve with one of the 5 options given to you. Okay, but let's look at something a little bit more challenging now. Okay, I forgot about this actually, and this is an important one to look at. We're still in the field of examining solution curves, but this is presented in a different way. This is the sort of question that's come up recently. So you could expect something like this. So here is a slope field. We're not given the rule for the DE, and that's fine. Okay, we know that the point on the solution curve goes through -2.5, 1.5. A point that it could also pass through is one of those 5 options. So we need to carefully trace from the point -2.5, 1.5. So let's just find where that is. And thankfully they've given us grid lines. There's -2, -2.5, up to 1.5 would be this point right there. Okay, so let's mark it nice and boldly. All right, so that's where we're starting in our curve, and then we're going to start to piece out the direction of the slope field from there. So let's just make sure that's -2.5 and 1.5. Okay, good. All right, let's do our best to start to create a line from there. So we're going to trace it around here and follow the curve around. All right, so I've done my best to trace a curve being corralled left and right from my single point that I started with, -2.5, 1.5. Okay, and let's now have a look at our options. I've moved, because you can see all the x values are pretty much positive. So did it go through 0? No, it didn't. Did it go through 1, 2? No, it's nowhere near a y value of 2. What about 3, 1? 3, 1 is up here. No, can't be 3, 1. That's not a bad match. This one looks pretty okay. And what about minus a half 2? No, that's up here. So that's has to be D. D is the only valid way you can come up with an answer. So you can expect those sort of questions as well. All right, but as I suggested, a more likely sort of question is, here's the slope field. What are the 5 differential equations that are represented? Here are 5 DEs. Which one out of the 5 is representing the slope field you see? So we're going to get onto that now. Okay, matching the slope field with a DE, as in one of the 5 presented to you. Now it's all about looking for patterns in the slope field. So here are some of the leading questions to ask yourself. So, okay, so if the DE consists of slope line segments that are uniform in the vertical direction, so as you can see in the example before you, let me just grab my pen. So you can see they all have the same steepness uniformly in the vertical direction. Doesn't matter where I go to for what value of x. If I look at various values of y, you know that it's unchanging. It's uniform vertically. So uniform. Uniform. Okay. So what does that mean? You know for a fact your dy dx must be a function of x. All right, so that's one way to eliminate potential candidates. So you're looking for dy dx being a function of x only, because you can see the steepness is dependent on x values, not on y values. So you'll always get that feature of being uniform in the vertical direction. I hope that makes sense. Now, of course, there might be several choices where dy dx is a function of x only, and then you'll look for other clues, but we'll be talking about those in a minute. Okay, so here's another slope field, and what you'll notice is all the line segments are sloped uniformly in the horizontal direction. So I'll just highlight that again. So let's just pick on y equals 2. You can see every line segment there corresponding to y equals 2 has a uniform slope to it. Y equals minus 2. Let's just look at this last one down here. Beyond minus 2, uniformed in the horizontal direction. So uniform slopes in that direction. Okay, what does that mean? That means our differential equation is a function of y only. There it is. It's a function of y only. All right. So you can see it's dependent only on y. It's independent of its x value, so it's a function of y only. Hopefully that makes sense to you. And of course, you might have a couple of options that are a function of y only. Then we need to look for further clues. Okay, hopefully that's all good. Okay, now what happens if the slope line segments are neither vertically or horizontally uniform? What do you know then? You know, of course, the DE is a function of both x and y. In that case, you're looking for other clues, and these clues will come into play later as well for more than one function of x, more than one function of y. Okay, what your eye should go towards is where you get perfectly flat line segments. So I'll just grab my pen just to highlight that. Perfectly flat line segments. That's something your eye should gravitate towards. Why? Because it's indicating places where your gradient rule is 0. Okay, very important that. So you can pick up on what your rule might be from that alone. Okay, what's next? Okay, now on the flip side, when your vertical line segments are perfectly steep, what would that indicate? Perfectly steep line segments. That's of course when your dy dx is undefined, when you have division by 0 issues. Division by 0. Very important. So you're able to pick up where they're occurring and how it can match one of the options given to you. All right, moving on. Okay, now you'll get situations where your slopes are positively sloped and when your line segments are negatively sloped. Okay, so when they're positively sloped, it's where your dy dx expression is positive. When they're negatively sloped, it's where your dy dx expression is negative. Makes sense, but that's going to help you piece together which is the right option to choose. Okay, so how does the pattern from flat to steep lines fit the rule? Okay, so these are all factors that can come into play. You're a detective, don't forget, and it's up to you to use the clues in the slope field to identify the correct DE. All right, let's consider this DE for instance. Okay, we've got a bunch of options. Now you can see they're all functions of x, so that's not helping us eliminate one or the other. And you can see they're all uniform vertically, matching each being a function of x. So what can we look for? Okay, what we're going to do is look at where the gradient is equal to 0, and it's 0 at those particular values of x. So let me just highlight. So perfectly flat, slightly out of alignment this one, but perfectly flat when x is equal to 0, and when x is plus or minus pi on 2. So it's slightly out of alignment this, which is a bit annoying, and that's where your eye gets cast to perhaps. Okay, so having a look at our rule, what can we eliminate? So obviously A would satisfy that because we know sine is 0 at 0 or pi. So, but of course we can eliminate B. That's gone. We can eliminate D. And what about E? We can also eliminate E, can't we? Because when x is 0, that's fine. But when x is pi on 2, it's recording it as sine pi on 4, which is certainly not equal to 0. So really, that one feature alone is helping us eliminate it to A or B. So where do we go to next? All right, we look for when dy dx is positive and when dy dx is negative. So you can see in this region here, when x is greater than 0, so this is all positive. So positively sloped. Okay, and when x is negative between 0 and minus pi on 2, in this region here, every slope is negatively sloped. Negative. Okay, so now that should help us inform the right choice. So dy dx. So we know from 0 to pi on 2, sine is, from 0 to pi, sine is always positive. So from x equals 0 to pi on 2 for sine 2x, it must be always positive. So it can't be A, it must be C. Okay, that's the only way it could be because that's positive for positive values of x from 0 to pi on 2 and negative for negative values of x. Hopefully that's making sense how we're able to eliminate the other options. So, and of course, yes, we knew that anyway, but that's not really helpful. The answer is equal to C. Okay, let's have a look at this one. It's a directional field. So feel free to pause at any point if you want to have a go on your own, but let's have a look at it. So the first obvious characteristic that I'd like to highlight would be the fact that, again, our slopes are uniform in the vertical direction, which means our dy dx must be a function of x only. Have a look anywhere you like. Let's have a look over here. Uniform vertically, so it's not dependent on y at all, only on x. So anytime I see dy dx as a function of y, I can eliminate it. And in one foul swoop, I've eliminated 3 out of 5. So it must be a function of x. So that's a poor looking x, isn't it? Okay, let's move on to some other features. Okay, how can I determine if it's x squared or x? Okay, where is my zero gradient? Okay, let's just highlight that. I might grab green for that. So you can see flat slopes at x equals 0. That's not really making us helping us distinguish whether it's x squared or x at this point. So let's keep going. All right, where is it positive? It's positive for positive values of x. All right, so we can just grab whenever x is positive. Whenever x is positive, you've got positive slopes, and whenever x is negative, you've got negative slopes. So negative. Okay. Now the only possible option for that, of course, would be dy dx is equal to x. Okay, because otherwise if it was dy dx equals x squared, it would be positive everywhere. Okay, so this is obviously the choice. Based on that decision alone, we can eliminate, oh, yes, we can eliminate A. All right, so let's see what other features I've got there listed. So dy dx is increasing as x is increasing. That's a feature that could be useful, but of course, it's happening, dy dx mod, so that's an interesting, to say it's getting steeper as you're moving away from x equals 0 to the right or to the left. So that might have been a feature that could help us inform us, but in fact, we didn't need to go there at all. So the answer must be C, as you can see, and it's a function of x, as I said. Answer must be equal to C. Good. All right, guys, let's have a look at this particular slope field. Okay, so first glancing up and down, left and right, it's certainly not uniform in the horizontal direction, moving left and right. It's not uniform in the vertical direction. The slopes are changing in both directions. What does that mean? Of course, it means our dE is a function of x and y. So wherever we see it as a function of just x, such as b, such as d, and such as E, we can eliminate it. Wow, isn't that neat? So we're down to two choices after that one decision-making process. So it's not always going to work out that neatly for you, but it has in this particular case. So let's get back to what else we can observe. So we can see, in fact, that you have zero gradient. dy dx is equal to 0 along that sloped section, along y equals minus x or some multiple of y equals minus x. Okay, so what is that matching? Okay, so it's 0 whenever x and y. It looks like in fact that it would be A. If that slope is representing the line y equals minus x, when x and y are negative opposites of each other, they're going to cancel each other out. And of course, what you're going to get is, let me just grab my pen, you're going to get this situation where dy dx ends up being equal to 0. So that's looking the most likely candidate. Okay, what else can we see here? All right, so some other features, dy dx is, okay, so all right, so we've already discussed that. That's looking the most likely situation. Of course, if x and y, if this is the point, say, minus 3, 3, clearly that would give you over here a slope of minus 1, and that's giving us a flat slope. So I'm pretty confident that A is the right choice at this point in time, but let's just keep clicking through the features I've got listed to see if there's any further evidence. No, there's not really. So I think that's pretty conclusive in itself. So noticing those flat slopes, there are no vertical slopes, but that is the standout feature to observe when making that decision. Can't be C because any point along that line would not make my dy dx equal to 0. Only points with y and x being negative opposites of each other would you produce a 0 result for dy dx. So hopefully that makes sense as well. All right, let's move on. All right, this might be a good one to finish with. I've got a couple of more slides, but maybe I'll save them for class when I see you again. Okay, it's a wacky looking slope field, I think you'd agree, over an interval -6 to 6 in the x and -6 to 6 in the y. And we've got DEs not all classically set up with dy dx the focus, but regardless, it shouldn't matter. It's still the same set of criteria in which to examine each of those candidates with regards to the given slope field. So we're told each of them contains a parameter. That might throw some of you. M is a parameter. It's some value that's not just positive, but also bigger than 1. That might be significant. So when you see M in the expressions, don't get thrown. It's just a number, just a constant. So that's how we have to treat it. Okay, let's begin. So as we said, a good place to start is to examine each of the line segments left to right. So if they're uniform, it's a function of y only, and clearly they're not. Okay, let's just have it capture that by looking at the top row. Clearly they're not uniform as a function, uniform horizontally, so they're not just a function of y. And if I look vertically, they're not uniform either. They're changing, so it's not a function of x either. So wherever I see dy dx being a function of just x or just y, I can eliminate it. So let's have a look. Let's have a look at A as a candidate. Well, dy dx is in the picture. Only x, not y. M is a parameter. We can treat it like a constant. So that can disappear. That can't be a candidate for the DE representing this slope field. What about the next one? Same deal. It's a function of x only, not a function of y. So we can eliminate it. Don't forget, M is just a parameter. Okay, just a constant. What about C? C is a function of x and y. So that's a potential candidate, as is D, as is E. So we've eliminated 2 from our initial thinking on uniform slopes horizontally and vertically. Okay, what else can we observe? The first thing I like to do, and it's not necessary to follow this routine, but I like to look where the slopes are flat, indicating values of xy points where dy dx is equal to 0. And you can see whenever x is equal to 0, dy dx is equal to 0 as well. Okay, so those flat slopes are indicating dy dx is equal to 0, and each of those have consistently the feature that x is equal to 0. So if I look back on my candidates, okay, when x is equal to 0, dy dx is equal to 0, so C is alive as a candidate. D is alive as a candidate. Okay, but E, what happens when I substitute x equals 0 into the candidate E? I get division by 0. If E was potentially correct, then that'd all be vertically sloped, not horizontally sloped. So I can eliminate E. Out it goes. Okay, speaking of vertical slopes, let's have a look where our slopes are vertical, and they occur along this line when y is equal to 0. Okay, so that's matching, confirming that C and D are viable candidates. Okay, because when y is equal to 0, I get division by 0 in both cases. So let's just highlight where we're up to. So we've looked at features where the gradient is equal to 0, where you're undefined. What else can we draw on to work out the right candidate from here? It's about looking at when slopes are positive and slopes are negative. Okay, so you can see over here, when x and y are both positive, you've got, you've got negatively sloped graphs. When x is positive and y is negative, you've got positively sloped. Okay, just looking at the various quadrants, they all have these features. Okay, when x is negative and y is positive, you've got a positive slope, and of course, when they're both negative, you've got the feature that your slopes are negatively sloped. They're negative. Okay, good. So these are negative and these are positive. All right. So what could match those situations? So we know M is a positive value. In fact, it's greater than 1, making it positive. Now, if it was C, does that match the situation? So in the first quadrant, X and Y are both positive. So if m is also positive, it's suggesting that dy dx would be positively sloped in the first quadrant. So it seems to be a mismatch. Let's have a look at d. Okay, it's x on y, so let's consider x and y in the first quadrant. Let's say that point there. So x is positive, y is positive, m is positive, but it's being multiplied by -1. It seems to be matching d. And of course, it's working also when x and y are both negative. X divided by y, negative on negative is positive, times by positive m multiplied by -1. Yes, d must be the candidate. Can't be c because it's not matching the direction of the line segments. So we've got our answer. So what have we got there yet? So I've discussed about that, and that's all about the direction of each slope in the various quadrants, matching only D and not C. So leading us to the correct answer, D. All right, that's it for now. I think I'll leave the next 2 slides for when I see you again. Hopefully that's enough for you to have a good crack at the work in the worksheet on slope fields. There, as I said, the actual questions in the textbook are pretty poor, but if you do those questions on the worksheet, it'll prepare you well for the exam and anything we might throw at you on the SAC. Okay, that's it for now. Enjoy the rest of your break. See ya.